something unusual is happening to Earth. And the first place it appeared was not in the sky, but inside a quiet laboratory in Boulder, Colorado. Atomic clocks measuring the vibration of cesium atoms about 9 billion cycles every second noticed that the planet had completed its rotation slightly early. Only about 1.5 milliseconds, yet enough to concern scientists responsible for GPS navigation, satellite orbits, and global timekeeping. In this exploration, we will follow the evidence hidden inside Earth's oceans, atmosphere, and deep iron core. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would truly mean a lot to me. It may look like a small thing, but I accept it with deep appreciation, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still reach generous hearts like yours. We begin with the question, why did the Earth suddenly spin faster, and why did atomic clocks notice this before humans? A quiet instrument in Boulder, Colorado noticed something unsettling long before any human sense could possibly detect it. In a laboratory operated by the National Institute of Standards and Technology, atomic clocks were calmly counting the oscillations of cesium atoms, more than 9 billion vibrations every second, when their measurements revealed that the Earth had completed one full rotation slightly ahead of schedule. The difference was small, roughly 1.5 milliseconds. Yet, for scientists responsible for the world's timekeeping systems, that tiny advance immediately drew attention, because even a fraction of a millisecond can ripple through satellite navigation, financial transactions, and the synchronization of global communication networks. Human perception cannot feel a difference of 1 millisecond in the length of a day. Our bodies are guided by the rise of sunlight, the cycle of sleep, and the turning of seasons. But the instruments built over the past 70 years operate in a different realm of precision. Atomic clocks, first demonstrated in the mid-1950s, measure time by observing transitions inside atoms themselves. In the case of cesium-133, the international definition of a second corresponds to exactly 9,192,631,770 oscillations of microwave radiation associated with a particular energy transition of that atom. That number, adopted by the International System of Units in 1967, forms the foundation of modern timekeeping. Inside the Boulder laboratory, lasers cool clouds of cesium atoms to temperatures just above absolute zero. These atoms are gently tossed upward inside a device known as an atomic fountain. As they rise and fall through a microwave cavity, the atoms respond to extremely precise electromagnetic frequencies. When the frequency matches the natural resonance of the cesium transition, the atoms change energy states in a predictable way. By locking an oscillator to this resonance, scientists create a clock so stable that it would lose or gain less than a second over tens of millions of years. Such precision allows scientists to compare the ticking of atomic time with the rotation of the planet itself. For most of human history, time was defined directly by Earth's spin. Ancient astronomers divided the day according to the motion of the sun across the sky, and mechanical clocks were calibrated to match that daily rhythm. Yet Earth does not rotate with perfect uniformity. Even in the 19th century, astronomers noticed irregularities in the length of a day when observing the transits of stars across telescopes. By the mid-20th century, these irregularities became clearer. In 1955, Louis Essen and Jack Parry at the United Kingdom's National Physical Laboratory built the first practical cesium atomic clock. Soon after, scientists compared its measurements with astronomical observations of Earth's rotation and discovered that the planet's spin was drifting by milliseconds over time. This realization led to a historic change in 1972, the adoption of Coordinated Universal Time, or UTC, which blends atomic time with Earth's rotation by occasionally inserting leap seconds to keep them aligned. For decades, the pattern was familiar. The gravitational pull of the Moon gradually slows Earth's rotation through tidal friction. Ocean tides move enormous volumes of water around the planet, and the interaction between ocean basins and the Moon's gravity extracts rotational energy from Earth. Over geological timescales, this process lengthens the day. Fossil records from coral growth rings suggest that hundreds of millions of years ago, a day lasted only about 22 hours. The Moon, meanwhile, slowly moves away from Earth at a rate of about 3.8 centimeters per year, carrying angular momentum outward in the Earth-Moon system. Given that long-term trend, scientists expected the planet's rotation to continue slowing slightly over time. Yet the measurements collected since about the year 2020 have shown something unexpected. Several of the shortest days ever recorded by modern instruments have occurred in just the past few years. On July 19, 2022, Earth completed its rotation approximately 1.59 milliseconds faster than the standard 24-hour day of 86,400 seconds. Other record-breaking days followed in 2023 and 2024, each slightly shorter than average. To appreciate why such tiny differences matter, consider how global positioning systems operate. GPS satellites orbit roughly 20,000 kilometers above Earth and transmit timing signals derived from onboard atomic clocks. Receivers on the ground compare the arrival times of these signals from multiple satellites. Even a nanosecond of timing error corresponds to a positional uncertainty of about 30 centimeters. When billions of devices from aircraft navigation systems to financial trading networks depend on synchronized time signals, the stability of the global clock becomes essential. For that reason, international organizations such as the International Earth Rotation and Reference Systems Service monitor Earth's spin continuously. They combine astronomical observations, satellite laser ranging, radio telescope measurements of distant quasars, and atomic time comparisons to determine the exact orientation and rotation rate of the planet. These measurements reveal variations not only in the length of a day, but also in the position of Earth's rotational axis. One technique uses very long baseline interferometry, or VLBI. Radio telescopes separated by thousands of kilometers simultaneously observe distant quasars, extremely bright galaxies powered by supermassive black holes. Because these quasars lie billions of light-years away, they appear fixed relative to Earth's rotation. By measuring the arrival times of radio waves at multiple telescopes, scientists can determine Earth's orientation in space with extraordinary precision, often to within fractions of a milliarc second. When those observations are compared with atomic time, they show that Earth's rotation is not perfectly steady. Atmospheric winds, ocean currents, shifting masses of ice and water, and movements deep within the planet all exchange angular momentum with the solid crust. Each of these processes can accelerate or slow the rotation slightly. Most variations occur on scales of microseconds or milliseconds. Physicist Richard Feynman once reflected on the subtle connections hidden within natural systems. He said, "Nature uses only the longest threads to weave her patterns." That idea captures the situation unfolding in these measurements. The shortening of a day by 1 millisecond is not an isolated event. It represents the combined influence of processes occurring across the entire Earth system, from the movement of air high in the atmosphere to the flow of molten iron thousands of kilometers below the surface. One possibility involves exchanges of angular momentum between the atmosphere and the solid Earth. When powerful jet streams shift direction, they redistribute mass around the planet. Because the total angular momentum of the Earth system must remain conserved, changes in atmospheric circulation can slightly speed up or slow down the rotation of the crust. Meteorological events such as El Niño have been shown to alter the length of a day by several microseconds. Another factor may lie in the oceans. Large-scale movements of water, including seasonal currents and long-term climate oscillations, shift enormous masses across the globe. Satellite missions, such as NASA and the German Aerospace Center's GRACE mission, have mapped these mass redistributions by measuring tiny changes in Earth's gravitational field. When ice melts in polar regions or groundwater moves across continents, the distribution of mass changes, and with it, the moment of inertia of the planet. A familiar example from physics illustrates this effect. When a spinning figure skater pulls their arms inward, their rotation rate increases. The total angular momentum remains constant, but the reduced distribution of mass allows the body to spin faster. Earth behaves similarly when mass moves closer to or farther from the rotation axis. Even deeper processes may contribute. Beneath the crust lies the mantle, and below that the outer core, a vast ocean of liquid iron and nickel, extending roughly 2,200 kilometers in thickness. This metallic fluid circulates due to convection driven by heat escaping from the inner core. The motion of this electrically conducting fluid generates Earth's magnetic field through the geodynamo process. As these currents shift, they can exchange angular momentum with the mantle above them. Geophysicists refer to this interaction as core-mantle coupling. Over periods of years or decades, changes in the flow of molten metal can subtly alter the speed of Earth's rotation. Measurements of Earth's magnetic field sometimes reveal variations that correspond with small changes in the length of a day. Each of these mechanisms operates simultaneously, making the interpretation of recent observations particularly complex. A day shortened by 1 millisecond may reflect the combined effect of atmospheric circulation, ocean currents, melting ice sheets, and motions deep inside the core. Untangling these contributions requires combining data from satellites, seismic networks, oceanographic measurements, and geodetic instruments distributed around the world. The emerging picture reveals something remarkable. Earth's rotation is not governed by a single process, but by the interaction of many systems across the entire planet. The atmosphere, oceans, ice sheets, mantle, and core all participate in an ongoing exchange of angular momentum. Instruments sensitive enough to detect atomic transitions now provide a window into these hidden dynamics. For scientists studying planetary physics, the recent shortening of days, therefore, raises an intriguing possibility. Could the acceleration observed since 2020 signal a temporary shift in one of these large-scale systems? Or might it represent the combined result of several smaller influences acting at once? The measurements themselves do not yet reveal the answer, but they point toward a deeper investigation of the forces shaping Earth's rotation. And as researchers look more carefully at these forces, one detail becomes increasingly hard to ignore. For billions of years, the Moon has slowly acted as a brake on Earth's rotation. Yet the newest measurements now hint that, at least for a short time, something within the Earth-Moon system may be doing the opposite, subtly pushing the rotation forward instead. For billions of years, a silent gravitational partnership between Earth and the Moon has controlled the rhythm of our planet's rotation. Yet the latest measurements show something unexpected. The Earth has recently begun to rotate slightly faster again. If the Moon has spent 4.5 billion years slowing the planet down, what force inside this system is now pushing in the opposite direction? To understand why this change is so surprising, it helps to begin with one of the most stable physical relationships in the solar system. The Earth-Moon system is governed by gravity and angular momentum. These two principles work together in a slow exchange of energy that has shaped the length of a day for nearly the entire history of our planet. The Moon formed about 4.5 billion years ago after a collision between the early Earth and a Mars-sized body, often called Theia. Evidence for this event comes from isotopic similarities between lunar rocks collected during the Apollo missions and Earth's mantle material. Once the debris settled and the Moon condensed, it orbited much closer to Earth than it does today. Geological modeling suggests that the early Moon may have been only about 20 to 30,000 kilometers away, compared with today's average distance of 384,400 kilometers. At that distance, the Moon's gravitational pull was dramatically stronger. The tides raised in Earth's early oceans were enormous, possibly hundreds of meters high. Every rotation of the planet dragged those tidal bulges slightly ahead of the line connecting Earth and Moon. Because Earth rotates faster than the Moon orbits, the bulge is pulled forward. That misalignment creates a gravitational tug between the bulge and the Moon. This interaction produces what physicists call tidal friction. The moving oceans rub against the seafloor and continental margins. Energy from Earth's rotation is slowly converted into heat within the oceans. At the same time, angular momentum transfers outward to the Moon's orbit. The result is a gradual breaking of Earth's rotation. At the same time, the Moon is pushed slightly farther away. The physics behind this exchange was studied in detail during the 19th century by George Darwin, son of Charles Darwin. He developed the first mathematical description of tidal evolution in the Earth-Moon system. Modern satellite measurements have confirmed the long-term result of this process with extraordinary precision. Laser reflectors left on the Moon by the Apollo missions allow scientists to measure the distance to the Moon by timing how long it takes laser pulses to travel there and back. These experiments show that the Moon is currently moving away from Earth at about 3.8 centimeters per year. That is roughly the rate at which human fingernails grow. This outward migration represents the steady transfer of rotational energy from Earth into the orbital motion of the Moon. Over geological time, this process lengthens the day. Fossil evidence preserves a remarkable record of that change. Certain coral species grow in daily and yearly patterns that can be counted in fossil skeletons. When geologists studied corals from about 400 million years ago, they discovered that the number of daily growth rings within a single year was larger than it is today. Instead of 365 days per year, those corals recorded about 400 days. That means each day was shorter than 24 hours. The explanation is simple. Earth was rotating faster in the past. The gradual slowing caused by tidal friction has been stretching the length of the day ever since. This long trend is one of the most stable predictions of celestial mechanics. Yet the present measurements show something curious. Over the last several years, Earth has produced some of the shortest days ever recorded with modern instruments. These variations are tiny, measured in milliseconds, but they represent a small acceleration compared with the long-term slowdown. The difference is temporary rather than permanent, but it demands explanation. If tidal friction is constantly draining rotational energy from Earth, then another process must occasionally return some of that energy back to the planet's rotation. The Earth-Moon system is not isolated from the rest of the planet's internal dynamics. Angular momentum can shift between different parts of the Earth's system. The solid crust, the oceans, the atmosphere, and the deep interior all participate in subtle exchanges. When mass moves closer to the rotation axis, the planet spins slightly faster. When mass moves farther away, the rotation slows. One well-known example involves the redistribution of water. Seasonal changes in ocean circulation move enormous volumes of water around the planet. When currents shift toward the equator or toward the poles, the distribution of mass relative to the rotation axis changes. Satellite missions such as the Gravity Recovery and Climate Experiment have observed these mass redistributions by measuring variations in Earth's gravitational field. Atmospheric circulation also contributes. The atmosphere carries roughly 5 quadrillion metric tons of air. When powerful jet streams accelerate or shift position, they exchange angular momentum with the solid Earth. If winds move eastward faster, the crust can slow slightly. If winds weaken or reverse patterns, the crust can gain rotational speed. These exchanges are small, but they occur continuously. The interaction between the Moon and the ocean still dominates the long-term trend. Yet, short-term fluctuations can temporarily reverse the slowdown. Scientists studying Earth rotation track these variations through a measurement known as the length of day parameter. This value records how much longer or shorter a particular day is compared with the standard duration of 86,400 seconds. Observatories around the world combine astronomical observations with atomic clock measurements to determine this value. The International Earth Rotation and Reference Systems Service publishes the official records. These measurements reveal complex patterns tied to atmospheric circulation, ocean currents, and interactions between Earth's mantle and core. Another subtle factor involves the gravitational influence of the Sun. Solar tides also raise bulges in Earth's oceans and atmosphere. Although the lunar tide is stronger, the solar tide can either reinforce or slightly oppose it depending on the positions of Earth, Moon, and Sun day. These alignments occur during new moons and full moons and create variations known as spring tides and neap tides. Even planetary gravitational effects contribute on extremely long timescales. The gravitational pull of Jupiter and other planets slightly perturbs the orbit of the Moon and the orientation of Earth's axis. These changes affect tidal patterns and therefore the long-term evolution of the Earth-Moon system. Despite all these influences, the tidal braking mechanism remains the dominant long-term force. Over millions of years, the day continues to lengthen. What scientists are observing now is a temporary fluctuation superimposed on that ancient trend. NASA researchers studying Earth rotation have described the phenomenon as part of the natural variability of the Earth system. Measurements from satellite laser ranging, global navigation, satellite systems, and radio astronomy all contribute to the analysis. One of the most precise techniques uses very long baseline interferometry. Radio telescopes, separated by thousands of kilometers, observe distant quasars simultaneously. Because quasars lie billions of light-years away, they provide stable reference points for measuring Earth's orientation and rotation. By comparing the arrival times of radio waves at multiple telescopes, scientists can detect variations in Earth's rotation, down to fractions of a millisecond. These measurements confirm that the planet's spin is influenced by many interacting systems. Ocean tides transfer energy to the Moon. atmospheric winds exchange angular momentum with the crust. Water redistributes across continents and oceans. Deep inside the planet, molten metal flows within the outer core. Carl Sagan once reminded audiences of the interconnectedness of planetary systems. He said, "Extraordinary claims require extraordinary evidence. The acceleration observed in recent years is not an extraordinary claim in itself. It is a small fluctuation within a complex physical system. Yet understanding the cause requires careful measurement and patient analysis. The Earth-Moon system therefore behaves like a vast mechanical arrangement where multiple components constantly exchange energy. The Moon acts as a persistent brake, but other processes occasionally press in the opposite direction. At present, the measurements indicate that these internal and surface processes are temporarily overcoming part of the lunar braking effect. The slowdown has not stopped. Over geological time, it will continue. But the recent acceleration reveals how dynamic the Earth's system truly is. And as researchers trace the source of that temporary push, attention begins to turn downward, far beneath the oceans and continents, toward a region nearly 3,000 kilometers below the surface where immense rivers of liquid iron circulate through the outer core. Could rivers of liquid iron 2,000 miles beneath your feet be rewriting the length of a day? 2,000 miles beneath the ground we walk on every day, an immense ocean of liquid metal is in constant motion, and scientists have begun to suspect that its slow currents may be quietly influencing the speed at which our entire planet rotates. Atomic clocks have revealed that the length of a day can shift by tiny fractions of a millisecond. To human perception, that change is invisible. Yet when researchers compare those measurements with models of Earth's interior, a remarkable possibility appears. The answer may lie far below the crust, in the outer core, where rivers of molten iron circulate through the deep interior of the planet. The structure of Earth is layered like a series of shells formed during the early history of the solar system. At the center lies the inner core, a solid sphere composed primarily of iron and nickel. Surrounding it is the outer core, a vast region of liquid metal extending from about 2,900 kilometers below the surface to roughly 5,100 kilometers deep. This outer core is not static. It behaves more like a slowly moving ocean made of molten iron, heated from below and stirred by convection. Temperatures in this region exceed 5,000 degrees Celsius. At those temperatures, iron remains liquid even under immense pressure. Heat escaping from the inner core drives convective motion, causing the molten metal to circulate in complex patterns. These motions are influenced by the rotation of the planet, which organizes the flow into swirling columns aligned roughly with the axis of rotation. This moving metal performs a critical function. It generates Earth's magnetic field through a process known as the geodynamo. As electrically conducting fluid moves through an existing magnetic field, it induces electric currents. Those currents in turn produce additional magnetic fields. The result is a self-sustaining dynamo that maintains the magnetic shield protecting Earth from charged particles streaming from the Sun. Observations from satellites operated by the National Aeronautics and Space Administration and the European Space Agency have mapped subtle changes in the magnetic field over decades. These variations reveal that the flow of liquid iron inside the outer core is not constant. Large-scale currents shift direction and intensity over time. In some regions, the magnetic field weakens, while in others, it strengthens. One example is the region known as the South Atlantic anomaly. Satellite instruments have detected a noticeable reduction in magnetic field strength over parts of South America and the South Atlantic Ocean. Researchers interpret this change as evidence of evolving flow patterns within the outer core. These patterns reveal that the interior of Earth is far more dynamic than once imagined. The discovery that the core is actively changing opened the possibility that its motion might influence the rotation of the entire planet. The outer core contains enormous mass. Even small changes in the movement of that mass can exchange angular momentum with the mantle above it. The mantle is the thick rocky layer that lies between the core and the crust. Although it behaves like solid rock on human timescales, over geological periods it flows slowly, almost like a very viscous fluid. The boundary between the liquid outer core and the solid mantle is therefore an interface where motion can transfer energy between layers. Geophysicists refer to this interaction as core-mantle coupling. When the flow of liquid metal shifts inside the core, it can exert torque on the base of the mantle. In response, the mantle and crust may accelerate or slow slightly relative to the deeper interior. This exchange does not require dramatic motion. A small redistribution of angular momentum within the core is enough to produce measurable effects on the rotation of the crust. Atomic clocks are sensitive enough to detect those changes. Evidence for this connection began emerging in the late 20th century, when scientists compared variations in Earth's magnetic field with changes in the length of the day. Researchers noticed that certain patterns appeared together. Periods when the magnetic field changed more rapidly sometimes coincided with small fluctuations in Earth's rotation rate. In 1996, geophysicists working with geomagnetic data proposed that decadal variations in the length of a day might reflect interactions between the core and the mantle. The idea gained support as more precise magnetic field measurements became available from satellites such as CHAMP, SWARM, and other missions dedicated to studying Earth's magnetism. These observations revealed waves of magnetic change moving through the outer core at speeds of several tens of kilometers per year. Scientists call these features torsional oscillations. They represent bands of liquid metal accelerating or decelerating relative to surrounding regions. When such waves travel through the core, they redistribute angular momentum inside the planet. That redistribution can slightly alter the rotation rate of the outer layers. The effect is extremely small, typically measured in fractions of a millisecond. Yet those tiny variations match the scale detected by atomic timekeeping systems. Researchers studying these oscillations use mathematical models of magnetohydrodynamics, the branch of physics describing the motion of electrically conducting fluids. By combining magnetic field observations with simulations of the core's fluid dynamics, scientists can estimate how these internal flows interact with the mantle. One of the remarkable aspects of this research is the indirect nature of the evidence. No instrument can travel into the outer core. The region lies thousands of kilometers below the surface under pressures millions of times greater than atmospheric pressure. Yet the behavior of that hidden ocean becomes visible through its influence on the magnetic field and the planet's rotation. Seismology provides additional clues. When earthquakes occur, seismic waves travel through the interior of Earth. Some waves pass through the mantle and outer core before reaching detectors around the globe. By analyzing how these waves change speed and direction, scientists reconstruct the structure of the deep interior. Data collected over decades have revealed that the outer core is fully liquid while the inner core remains solid. The contrast between those two layers supports the idea that fluid motion within the outer core can exchange momentum with the mantle above. Researchers have also observed that the length of a day varies on several time scales. Some fluctuations occur over seasons, influenced by atmospheric circulation and ocean currents. Others unfold over decades, which is the timescale expected for core mantle interactions. These longer cycles are especially intriguing because they correspond to the time required for large-scale flow patterns to evolve inside the core. In several studies published in geophysical journals, scientists have identified correlations between magnetic field changes and decadal variations in Earth's rotation. Carl Sagan once described the scientific process with a simple observation. He said, "Somewhere, something incredible is waiting to be known." The exploration of Earth's deep interior illustrates that idea clearly. The clues are subtle. The signals appear as tiny variations in magnetic intensity or fractions of a millisecond in the length of a day. Yet together, they reveal the presence of powerful forces operating far beneath the surface. These forces move slowly compared with atmospheric storms or ocean waves. The currents of molten iron travel at speeds measured in kilometers per year rather than meters per second. But the mass involved is immense. The outer core contains more than 1/3 of Earth's mass. Even gradual motion within that region carries enormous momentum. When the pattern of circulation changes, the redistribution of that momentum can reach the mantle and crust. The result is a subtle shift in the rotation of the planet. Scientists continue to refine models of these interactions using supercomputers capable of simulating fluid dynamics under extreme conditions. These models incorporate data from magnetic field observations, seismic studies, and measurements of Earth's rotation. Each new dataset helps reveal a clearer picture of the deep interior. The emerging view is that Earth behaves as a connected system, extending from the atmosphere above the surface to the molten metal thousands of kilometers below. Changes in one layer can influence the behavior of another through the exchange of energy and momentum. The shortening of the day observed in recent years may therefore reflect a complex combination of influences. Atmospheric circulation, ocean currents, melting ice, and internal core dynamics may all contribute to the variations detected by atomic clocks. Among these factors, the motion of liquid iron within the outer core stands out because it operates on timescales consistent with the recent measurements. When torsional oscillations redistribute momentum within the core, they can slightly accelerate the outer layers of the planet. Such adjustments do not last forever. Over longer periods, the gravitational interaction with the Moon continues to slow Earth's rotation. Yet within that broader trend, the internal dynamics of the planet can create temporary shifts in the opposite direction. The picture that emerges is both complex and elegant. Deep beneath the continents and oceans, a vast ocean of molten metal circulates through the outer core. Those currents generate the magnetic field that shields the planet. At the same time, they exchange momentum with the mantle, producing tiny adjustments in the speed of Earth's rotation. Atomic clocks, measuring time with extraordinary precision, have made these hidden processes visible. And as scientists investigate the internal dynamics of this molten ocean more closely, attention is beginning to focus on another intriguing possibility involving the solid iron sphere at the center of the planet and the surprising evidence suggesting that its motion may not always match the rotation of the surface. Above, did the solid iron heart of Earth quietly change direction? Far beneath the continents and oceans, deeper than any drill could ever reach, lies a solid sphere of iron roughly 1,200 kilometers in radius, and recent seismic research suggests that this hidden structure at the center of the planet may have changed the way it moves relative to the rest of Earth. If that interpretation is correct, the deepest layer of the planet could be subtly influencing how the entire world rotates above it. The inner core is one of the most extraordinary regions inside Earth. It is a solid object composed primarily of iron and nickel, surrounded by the liquid metal ocean of the outer core. The temperature in this region approaches 5,000 to 6,000 degrees Celsius, similar to the surface of the Sun, yet the pressure is so immense that the metal remains solid. At the center of Earth, the pressure exceeds 360 gigapascals. Under such conditions, atoms are packed together so tightly that iron crystallizes into a dense solid even at temperatures where it would normally melt. Despite being buried more than 5,000 kilometers beneath the surface, the inner core plays a central role in the behavior of the planet. It slowly releases heat as the Earth cools over geological time. That heat drives convection in the surrounding outer core, sustaining the geodynamo that produces Earth's magnetic field. Without that magnetic shield, charged particles from the Sun would gradually strip away the atmosphere and expose the surface to intense radiation. For many decades, scientists assumed that the inner core rotated at exactly the same rate as the rest of the planet. The idea seemed natural. The inner core is embedded inside Earth and held by gravity in the center of the planet. But beginning in the late 20th century, new observations suggested that the situation might be more complicated. The key evidence came from seismology. Every major earthquake sends waves traveling through the interior of Earth. Some of those waves pass through the mantle and into the core before reaching seismic stations on the opposite side of the planet. Because these waves interact with the materials they pass through, their travel times carry information about the structure and motion of Earth's deep interior. In 1996, researchers Xiaodong Song and Paul Richards from Columbia University analyzed seismic waves produced by earthquakes occurring in similar locations but separated by several decades. They noticed something unusual. Waves that traveled through the inner core arrived at detectors slightly earlier than expected when compared with older measurements. The interpretation was bold. The inner core might be rotating slightly faster than the rest of the planet. The difference was extremely small, perhaps only a fraction of a degree per year. Yet it suggested that the deepest layer of Earth could move independently from the mantle and crust above. This phenomenon became known as inner core superrotation. Over the following decades, scientists analyzed additional seismic records from earthquakes around the world. Some studies appeared to support the idea that the inner core rotated slightly ahead of the mantle. Other analyses suggested the motion might vary over time. Then, in 2023, new work by geophysicists studying seismic waves from repeated earthquakes raised another possibility. Researchers, including John Vidale at the University of Southern California, examined seismic signals produced by earthquakes occurring near the South Sandwich Islands. These earthquakes generated waves that traveled through the inner core before reaching detectors thousands of kilometers away. By comparing signals from events separated by many years, the team observed that the travel times no longer matched the earlier pattern, suggesting steady superrotation. Instead, the data indicated that the inner core may have slowed relative to the mantle, possibly even reversing the direction of its differential rotation. The idea does not mean that the inner core spins backwards in the everyday sense. Rather, it means that its motion relative to the mantle could change direction within a long oscillating cycle. The inner core may rotate slightly faster than the mantle for several decades, then gradually slow until its motion matches the mantle, and later shift to moving slightly slower before reversing again. In this view, the inner core behaves almost like a giant rotating component inside a complex mechanical system. John Vidal described the concept in a memorable way when discussing the findings. He said that the inner core acts like a flywheel inside the Earth. A flywheel stores rotational energy and can influence the speed of the machinery connected to it. When the flywheel shifts, the rest of the system eventually adjusts. That image captures the essential physics. The inner core contains enormous mass. Although it is small compared with the entire planet, it still holds roughly 1% of Earth's total mass. When that mass changes its rotational relationship with the mantle, angular momentum must be redistributed through the surrounding layers. The coupling occurs through both gravitational and electromagnetic interactions. The inner core interacts magnetically with the fluid outer core surrounding it. At the same time, gravitational forces between irregularities in the inner core and the mantle create torque that can exchange angular momentum between layers. Over decades, these forces may produce slow oscillations in the rotational behavior of the inner core relative to the rest of the planet. If such oscillations exist, they could influence the length of the day measured at the surface. When the inner core transfers angular momentum outward, the mantle and crust may accelerate slightly. When the transfer occurs in the opposite direction, the surface rotation may slow. The scale of these changes is extremely small. Variations in the length of a day are typically measured in fractions of a millisecond. Yet modern atomic clocks are sensitive enough to detect them, and global geodetic networks continuously monitor Earth's rotation with extraordinary precision. Understanding the behavior of the inner core remains one of the most challenging problems in geophysics. Direct observation is impossible. No instrument can descend 5,000 kilometers through the mantle to reach the core. Instead, scientists rely on indirect evidence gathered from seismic waves, magnetic field observations, and precise measurements of Earth's rotation. Seismic imaging continues to improve as global networks of detectors grow more sensitive. Thousands of seismic stations now record earthquakes across the planet. Each new event provides additional data about the materials and structures deep within Earth. Meanwhile, satellite missions operated by the National Aeronautics and Space Administration and the European Space Agency monitor variations in Earth's gravitational field and magnetic field. These measurements help scientists track mass movements within the planet and changes in the flow of liquid metal in the outer core. Together, these datasets reveal a planet that is far from static. Beneath the crust, enormous masses of rock and metal are in constant motion. Heat from Earth's interior drives convection in the mantle. Liquid iron circulates through the outer core. The inner core slowly crystallizes as the planet cools over billions of years. All of these processes interact through gravity, pressure, and electromagnetic forces. The result is a dynamic interior where even the deepest layers can influence the behavior of the surface. Carl Sagan once observed that understanding a planet requires looking beneath its surface. He said, "Somewhere, something incredible is waiting to be known." The study of Earth's inner core illustrates that principle clearly. Each improvement in measurement reveals another layer of motion hidden within the planet. The suggestion that the inner core may have changed its rotational behavior does not yet represent a final conclusion. Different research groups analyzing seismic data sometimes reach different interpretations. The signals are subtle, and the structure of the inner core itself may be complex, possibly containing variations in crystal orientation or composition. Yet the emerging evidence points toward a deeper understanding of how Earth's internal layers interact. If the inner core truly behaves like a slowly oscillating flywheel, then its motion may be one of the mechanisms capable of redistributing angular momentum throughout the planet. Such exchanges could contribute to the small fluctuations in the length of the day now measured by atomic clocks. And while scientists continue to analyze seismic records searching for clearer patterns in the motion of Earth's deepest layer, another influence on planetary rotation is unfolding much closer to the surface, where enormous volumes of water are being redistributed across the globe as polar ice melts and oceans slowly reshape the balance of mass around the spinning Earth. Why would melting ice at the poles change the length of a day? A shift in the speed of Earth's rotation can begin with something that appears far removed from planetary mechanics. It can begin with ice slowly melting along the coast of Greenland, or with glaciers retreating across Antarctica. These changes seem local when viewed from the ground, yet when scientists measure the motion of the entire planet with atomic clocks and satellite instruments, the redistribution of ice and water across Earth becomes visible as a subtle change in how the planet spins. To understand why this happens, researchers start with one of the most fundamental principles in physics, the conservation of angular momentum. When a rotating object changes the way its mass is distributed, its rotation rate must adjust. This rule governs systems ranging from spinning laboratory gyroscopes to the rotation of planets. The physics can be understood through a simple observation from everyday life. When a spinning figure skater draws their arms inward, their rotation speeds up. When they extend their arms outward, their spin slows slightly. The reason is that pulling mass closer to the center reduces the object's resistance to rotation, while spreading mass farther from the center increases that resistance. In planetary physics, the same principle applies, but on a vastly larger scale. Earth's mass is not perfectly fixed in place. Water moves constantly through the hydrological cycle. Ice accumulates during colder periods and melts during warmer ones. Ocean currents redistribute enormous volumes of water across the globe. Each of these movements alters the distribution of mass relative to the planet's rotation axis. The concept that describes this property is known as the moment of inertia. In simple terms, it measures how difficult it is to change the rotation of an object. When mass shifts outward away from the axis of rotation, the moment of inertia increases and the rotation slows slightly. When mass moves closer to the axis, the moment of inertia decreases and the rotation speeds up. For Earth, the polar regions play a particularly important role in this balance. Large amounts of the planet's frozen water are stored near the poles in the form of glaciers and ice sheets. Greenland and Antarctica together contain enough ice to raise global sea levels by tens of meters if it were completely melted. Over recent decades, scientists have observed that these ice sheets are losing mass at an accelerating rate. Satellite missions operated by the National Aeronautics and Space Administration and the European Space Agency have measured these changes with remarkable precision. One of the most influential missions in this field is the Gravity Recovery and Climate Experiment, known as GRACE. Launched in 2002, the mission consists of 2 satellites flying in formation around Earth. By measuring the tiny variations in distance between the spacecraft as they orbit, researchers can map subtle changes in Earth's gravitational field. Those changes reveal where mass is increasing or decreasing on the surface of the planet. When large amounts of ice melt from a glacier or ice sheet, the local gravitational field weakens slightly. The GRACE satellites detect this change and allow scientists to calculate how much ice has been lost. Measurements from the GRACE mission have shown that Greenland alone has been losing hundreds of billions of tons of ice per year during the early 21st century. Antarctica has also experienced substantial ice loss, particularly in regions where warm ocean water flows beneath floating ice shelves. When this ice melts, the resulting water does not remain at the poles. It flows into the global ocean system and spreads across the planet. Ocean currents gradually distribute the water toward lower latitudes, increasing the mass of the oceans closer to the equator. This redistribution has a direct effect on Earth's rotation. Moving mass away from the poles and toward the equator increases the planet's moment of inertia. According to the conservation of angular momentum, that change produces a small reduction in the rotation rate. The effect is extremely subtle. Changes in the length of the day caused by ice melt are measured in microseconds, millionths of a second. Yet modern timekeeping systems are capable of detecting even these minute variations. Global networks of atomic clocks track the exact length of each day with extraordinary accuracy. These clocks rely on the oscillation frequency of cesium atoms, which provide a stable reference for measuring time. When scientists compare the atomic timescale with Earth's actual rotation, tiny differences become visible. Researchers studying these differences have discovered that long-term trends in ice mass loss correspond with small changes in Earth's rotational behavior. The redistribution of water contributes to variations in the length of the day and to subtle shifts in the position of Earth's rotational axis. The motion of the rotational axis across Earth's surface is known as polar motion. Instead of remaining fixed, the axis wanders slightly over time. This wandering can be measured using satellite geodesy and ground-based observations. Changes in ice mass play a significant role in this motion. When large quantities of water move across the planet, they shift the center of mass of the entire Earth system. As a result, the rotational axis adjusts to maintain balance. Scientists at institutions including the Jet Propulsion Laboratory and the German Research Center for Geosciences have analyzed satellite data to quantify this effect. Their studies show that mass loss from glaciers and ice sheets is one of the dominant drivers of recent changes in polar motion. These findings demonstrate that processes occurring on the surface of the planet can influence its global rotation. The Earth behaves not as a rigid object, but as a dynamic system in which atmosphere, oceans, ice, and solid rock all interact. Another interesting aspect of this research is the timescale over which the effects appear. Ice sheets evolve over decades and centuries, meaning their influence on Earth's rotation accumulates gradually. Each year's melting adds a small increment to the redistribution of mass. When these increments are combined over long periods, the cumulative impact becomes measurable. Satellite records now span more than 2 decades, allowing scientists to track how the balance of mass across the planet changes year by year. Carl Sagan once summarized the spirit of scientific investigation with a simple statement. He said, "Science is a way of thinking much more than it is a body of knowledge." In the study of Earth's rotation, this way of thinking has allowed researchers to connect phenomena that might otherwise seem unrelated. A glacier melting along the coast of Greenland may appear to be a local environmental event. Yet when that melting transfers hundreds of billions of tons of water into the ocean, the mass of the entire planet is redistributed. The rotation of Earth responds to that redistribution according to the same physical laws that govern every rotating system. This perspective reveals the remarkable sensitivity of modern measurement systems. The change in the length of the day caused by melting ice is far too small to notice in daily life. Yet instruments designed to measure time with extreme precision detect the signal clearly. The same measurements also highlight the complexity of Earth's rotation. Ice loss is only one of several factors influencing the speed at which the planet spins. Atmospheric circulation, ocean currents, and internal processes within the core all contribute to variations in rotation rate. Understanding the combined effect of these influences requires integrating data from many different fields of science. Climate researchers study the evolution of ice sheets. Oceanographers analyze the movement of water masses across the oceans. Geophysicists model the behavior of Earth's interior. Together, these disciplines reveal a coherent picture of the planet as an interconnected system. Energy and mass move continuously through the atmosphere, hydrosphere, and solid Earth. Each movement contributes in small ways to the global balance of angular momentum. As satellite observations continue and new missions improve measurement precision, scientists are gaining a clearer view of how these processes interact. The redistribution of water through melting ice has already become one of the most important contributors to recent changes in Earth's mass distribution. And while the shifting of hundreds of billions of tons of water across the planet demonstrates how surface processes can influence the rotation of Earth, another surprising factor comes not from ice or oceans, but from human activity itself, where large-scale irrigation and groundwater extraction have begun to move enough water to alter the orientation of the planet's axis. Could human irrigation actually tilt the planet? A shift in the orientation of an entire planet might seem like the kind of event produced only by deep geological forces or massive cosmic impacts. Yet in recent years, geophysicists analyzing satellite data discovered something unexpected. The gradual movement of water, pumped from underground reservoirs for agriculture, has redistributed enough mass across Earth to slightly alter the position of the planet's rotational pole. The discovery emerged not from a single dramatic observation, but from decades of careful measurement revealing how human activity interacts with the physical laws governing planetary motion. The rotation of Earth can be imagined as a spinning system balanced around an axis that passes through the North Pole and the South Pole. In practice, this axis does not remain perfectly fixed. It shifts slightly across Earth's surface as mass moves within the atmosphere, oceans, ice sheets, and solid Earth. Scientists track this motion through a field known as geodesy, which measures the shape of the planet, its gravitational field, and its precise rotation in space. For much of the 20th century, changes in the rotational axis were attributed primarily to natural processes. Seasonal movement of water through the atmosphere and oceans causes small oscillations. Melting glaciers shift mass from polar regions toward the oceans. Movements inside Earth's mantle and core contribute additional influences over longer timescales. However, as satellite observations improved in the late 20th and early 21st centuries, researchers began noticing patterns that did not align perfectly with known natural mechanisms. The motion of the rotational pole appeared to shift steadily eastward during recent decades, and the magnitude of that shift required explanation. Understanding this phenomenon required examining how water moves through the global hydrological cycle. Fresh water exists in several major reservoirs including glaciers, lakes, rivers, soil moisture, and underground aquifers. Aquifers are particularly important because they store enormous quantities of groundwater accumulated over thousands or even millions of years. These underground reservoirs form when rainwater gradually infiltrates through soil and rock layers, collecting in porous formations beneath the surface. In many regions of the world, aquifers serve as the primary source of water for agriculture. Farmers pump groundwater to irrigate crops, especially in areas where rainfall alone cannot sustain large-scale food production. During the 20th century, irrigation expanded dramatically across many parts of the planet. Regions including northern India, the North China Plain, the High Plains aquifer system of the United States, and agricultural zones across the Middle East began extracting groundwater at increasing rates to support growing populations and expanding agricultural economies. Each pump may appear small when viewed individually, yet when millions of pumps operate across continents year after year, the cumulative movement of water becomes enormous. Water removed from underground aquifers does not simply vanish. It enters rivers, soil, and eventually the oceans after being used for irrigation or consumed by crops. This process effectively transfers water mass from land-based reservoirs to the global ocean system. When that transfer occurs, the distribution of mass across the planet changes. In physics, the rotation of an object depends not only on how much mass it contains, but also on where that mass is located relative to the rotation axis. When large quantities of water move from continental interiors toward the oceans, the center of mass of the Earth system shifts slightly. As a result, the orientation of the rotational axis adjusts in order to maintain the balance required by conservation of angular momentum. Scientists studying this effect relied on data from several satellite missions designed to monitor Earth's gravity field and surface motion. Among the most important was the Gravity Recovery and Climate Experiment mission developed through collaboration between the National Aeronautics and Space Administration and the German Research Center for Geosciences. The Gravity Recovery and Climate Experiment satellites measure tiny variations in the gravitational pull of Earth as they orbit the planet. These variations reveal where mass is increasing or decreasing across the surface. When large volumes of groundwater are removed from aquifers, the local gravitational field weakens slightly. The satellites detect the change and allow scientists to estimate how much water has been lost. Using these observations, researchers constructed global maps of groundwater depletion over several decades. The results were striking. Between 1993 and 2010, approximately 2,100 gigatons of groundwater were extracted from aquifers worldwide. 1 gigaton corresponds to 1 billion metric tons, meaning the total amount of water moved during that period exceeded 2 trillion tons. Such an enormous redistribution of mass inevitably influences the rotation of the planet. Geophysicist Ki Weon-seo and colleagues analyzed this data in combination with measurements of polar motion. Their research revealed that groundwater depletion contributed significantly to the eastward shift of Earth's rotational pole. During the period studied, the pole moved roughly 80 centimeters relative to Earth's surface, due in part to the transfer of water mass caused by irrigation. This shift may appear small when compared with the scale of the planet, yet the measurement represents a clear signal of how human activity can interact with fundamental planetary processes. The mechanism linking groundwater extraction to polar motion can be understood through the same physical principles that govern other rotating systems. When mass moves across the surface of a rotating body, the distribution of inertia changes. The rotation axis adjusts to maintain equilibrium. In the case of Earth, large-scale groundwater pumping effectively transfers mass from continental interiors toward the oceans. Because much of this water ultimately reaches lower latitudes through river systems and ocean circulation, the redistribution changes the balance of mass relative to the rotation axis. The resulting shift in polar motion is detectable through global geodetic networks that measure Earth's orientation in space. Observatories around the world monitor the positions of distant quasars using radio telescopes. These observations establish a stable reference frame against which Earth's rotation can be measured with extraordinary precision. Combined with satellite laser ranging, global positioning system measurements, and gravitational field data, scientists obtain a detailed picture of how the planet's rotation axis moves over time. These measurements reveal that the motion of the pole is influenced by multiple interacting factors, including atmospheric circulation, ocean currents, melting glaciers, and internal dynamics within Earth's mantle and core. Groundwater depletion has now been added to this list as a measurable contributor. Carl Sagan once reflected on the interconnected nature of scientific discovery when he said, "We are a way for the cosmos to know itself." Observations of Earth's rotation demonstrate how deeply interconnected the systems of our planet truly are. Activities occurring in agricultural fields across continents can influence the orientation of the entire world. This does not mean that irrigation alone controls the motion of Earth's axis. Rather, it contributes one component within a complex network of influences. Atmospheric winds exchange angular momentum with the surface. Ocean currents move vast masses of water across the globe. Melting ice redistributes weight between polar regions and equatorial oceans. Each of these processes adds its own signal to the motion of the rotational pole. The recognition that groundwater extraction plays a measurable role highlights the remarkable sensitivity of modern observation systems. Satellite missions, atomic clocks, and geodetic networks now detect planetary-scale consequences of processes that would have been invisible to earlier generations of scientists. At the same time, the discovery provides insight into the broader physics governing Earth as a rotating system. Mass redistribution anywhere within the Earth system contributes to changes in rotation and orientation. The planet behaves as a single dynamic structure in which atmosphere, oceans, ice, solid rock, and even human activity interact through the laws of physics. As researchers continue analyzing satellite data and refining global hydrological models, the influence of groundwater movement on Earth's rotation is becoming clearer. Each improvement in measurement resolution reveals new details about how water flows through the planet's reservoirs and how those flows alter the distribution of mass. Yet groundwater extraction represents only one part of the story. High above the surface, another massive reservoir of moving mass is constantly exchanging angular momentum with the planet below. The atmosphere itself carries enormous momentum through the motion of global winds, and when those winds accelerate or shift direction, they can transfer rotational energy between the air and the solid Earth. Can winds in the upper atmosphere steal energy from the entire planet? Every second of every day, an invisible ocean of gas moves above our heads, and the total mass of that ocean is so large that its motion can slightly alter the speed of Earth's rotation. When global wind systems accelerate or shift direction, they exchange angular momentum with the solid planet below. The resulting adjustment is extremely small, often measured in microseconds in the length of a day, yet it is large enough to be detected by the most precise clocks humanity has built. At first, this idea may seem surprising because air appears light and intangible in daily life. Yet the atmosphere is anything but small. The total mass of Earth's atmosphere is about 5.15 quadrillion metric tons. Spread across the surface of the planet, that mass exerts a pressure of roughly 100,000 pascals at sea level. In effect, the atmosphere forms a massive rotating shell surrounding the solid Earth. Because the atmosphere rotates with the planet, it carries angular momentum just as the oceans and the solid crust do. When winds change speed, the distribution of that angular momentum changes as well. The physical law governing the system is the conservation of angular momentum. When one component of a rotating system accelerates, another component must adjust so that the total angular momentum remains balanced. For Earth, this means that when large-scale winds strengthen in the direction of planetary rotation, the atmosphere gains angular momentum. To conserve the total, the solid Earth must slow slightly. When the winds weaken or reverse direction, the opposite transfer occurs, and the rotation of the planet speeds up by a tiny amount. These exchanges are subtle but measurable. Modern observations of Earth's rotation rely on networks of atomic clocks combined with geodetic measurements of Earth's orientation in space. Scientists compare the uniform flow of atomic time with the actual rotation of the planet, which varies slightly from day to day. Changes caused by atmospheric motion are typically on the order of microseconds. 1 microsecond represents 1/1,000,000th of a second. While this is far below human perception, it lies well within the sensitivity of global timekeeping systems used for satellite navigation, telecommunications, and scientific measurement. The mechanism linking winds to Earth's rotation operates through the circulation patterns of the atmosphere. The most important of these patterns occur in the upper troposphere and lower stratosphere, where powerful jet streams flow around the planet. Jet streams are narrow bands of strong winds located roughly 10 to 12 kilometers above the surface. They form where large temperature differences exist between air masses, particularly along the boundaries between polar and mid-latitude regions. The contrast in temperature creates pressure gradients that accelerate air into fast-moving currents. Typical wind speeds in jet streams can exceed 100 meters per second, and during intense weather systems they may become even stronger. Because these winds circle large portions of the planet, the amount of angular momentum they carry is significant. Scientists studying the interaction between the atmosphere and Earth's rotation developed a concept known as atmospheric angular momentum. This quantity measures how much rotational motion is contained in the moving air of the atmosphere. When researchers track atmospheric angular momentum using global weather data, they find a clear relationship with variations in the length of the day. When the atmosphere gains angular momentum through stronger eastward winds, the rotation of the solid Earth slows slightly. When atmospheric momentum decreases, the surface rotation speeds up. One of the earliest efforts to understand this relationship emerged in the 1970s and 1980s when improvements in global meteorological observations allowed scientists to analyze atmospheric circulation with greater detail. Meteorological centers began producing global wind datasets using weather balloons, aircraft measurements, and satellite observations. By combining these measurements with precise records of Earth's rotation, geophysicists demonstrated that fluctuations in atmospheric angular momentum correspond closely with short-term changes in the length of the day. These discoveries revealed that the atmosphere and the solid Earth form a tightly coupled system, exchanging momentum continuously. Large-scale climate phenomena can amplify this interaction. One of the most important examples is the El Niño Southern Oscillation. This climate pattern involves periodic warming of surface waters in the central and eastern Pacific Ocean, accompanied by shifts in atmospheric circulation. During El Niño events, trade winds weaken and large-scale wind patterns across the Pacific reorganize. These atmospheric changes modify the distribution of angular momentum in the atmosphere. Scientists analyzing historical records have found that strong El Niño events often coincide with detectable changes in Earth's rotation rate. The shifts are small but consistent with the expected transfer of momentum between atmosphere and planet. For example, studies conducted at the National Aeronautics and Space Administration and other research institutions have shown that variations in atmospheric circulation during major El Niño episodes can alter the length of the day by several microseconds. Although these numbers appear extremely small, they represent the collective effect of atmospheric motion occurring across the entire globe. The role of the atmosphere in influencing Earth's rotation highlights how interconnected the planetary system is. Winds generated by temperature contrasts in the atmosphere can ultimately influence the rotation of a planet with a mass of nearly 6 sextillion kilograms. This interaction also reveals the remarkable precision of modern measurement techniques. Instruments designed to track Earth's rotation must account for atmospheric angular momentum in order to maintain accurate time standards. Global positioning systems, satellite communication networks, and astronomical observations all rely on precise knowledge of Earth's orientation and rotation rate. Small changes caused by atmospheric circulation therefore become relevant to technologies used daily around the world. The data used to monitor these changes come from several sources. Satellite missions operated by the National Aeronautics and Space Administration and the European Space Agency measure atmospheric conditions across the globe. Weather satellites observe cloud patterns, temperature distributions, and wind velocities at different altitudes. At the same time, global networks of weather balloons provide direct measurements of wind speed and direction through the atmosphere. These observations feed into numerical weather prediction models that simulate the circulation of the atmosphere. By combining these datasets with precise measurements of Earth's rotation, scientists calculate the total angular momentum contained in atmospheric motion. This quantity fluctuates continuously as weather systems develop and dissipate across the planet. One particularly interesting aspect of this research is that the atmosphere acts as a dynamic interface connecting many components of the Earth system. Winds respond to temperature differences driven by ocean currents, solar heating, and the distribution of land and water across the surface. Changes in ocean temperature patterns, such as those occurring during El Niño events, therefore influence atmospheric circulation. That circulation then interacts with the rotation of the planet itself. Carl Sagan once emphasized the interconnected nature of planetary systems when he said, "If you wish to make an apple pie from scratch, you must first invent the universe." The physics of Earth's rotation reflects that same interconnectedness. Processes occurring in the atmosphere, oceans, and interior all contribute to the behavior of the planet as a rotating body. Atmospheric circulation is unique among these influences because it changes rapidly compared with processes in the mantle or core. Wind patterns evolve on timescales of days to weeks. As a result, the exchange of angular momentum between atmosphere and Earth can produce short-term fluctuations in the rotation rate. These variations are superimposed on longer trends produced by other mechanisms such as tidal interactions with the Moon, redistribution of water through melting ice, and movements within Earth's interior. Understanding the full picture requires integrating observations across many fields, including meteorology, oceanography, geophysics, and astronomy. Each dataset reveals a different aspect of the dynamic system governing the rotation of our planet. As measurement precision continues to improve, researchers are uncovering additional details about how atmospheric motion influences Earth's spin. The atmosphere may appear thin when compared with the mass of the solid planet, yet its global circulation carries enough momentum to leave measurable fingerprints in the timing of each day. And while powerful winds sweeping through the upper atmosphere show how moving air can exchange momentum with the planet, Earth displays another kind of motion as well. The planet's rotational axis slowly shifts over time, producing a gentle wobble that scientists continue to study in the exploration titled, "Why Does the Planet Wobble Like a Slightly Unbalanced Top?" The ground beneath our feet appears steady and unmoving, yet careful measurements reveal that the entire planet performs a slow and persistent wobble as it spins through space. Astronomers first noticed this motion in the late 19th century, and since that time the position of Earth's rotational pole has traced a gentle circular path across the surface of the planet. The diameter of that motion is only about 9 meters, yet it carries a profound message about how mass moves within the Earth system. The discovery began in 1891, when American astronomer Seth Carlo Chandler analyzed long records of astronomical observations. By studying the apparent motion of stars relative to observatories on Earth, Chandler realized that the position of the North Pole was not perfectly fixed. Instead, it drifted slowly in a circular pattern over time. This oscillation became known as the Chandler wobble. The motion repeats approximately every 14 months. When plotted on a map of Earth's surface, the path of the pole forms a small spiral pattern centered near the geographic North Pole. Although the movement covers only a few meters, the phenomenon carries immense scientific importance. The location of Earth's rotation axis determines how the entire planet spins in space. Even small shifts reveal that mass is moving within the Earth system. To understand why the wobble occurs, it helps to think about how a spinning object behaves when its mass distribution changes. A perfectly balanced rotating body maintains a stable axis. But if mass shifts slightly within the object, the axis begins to move relative to the surface. Earth is not a perfectly rigid sphere. It is a complex system composed of atmosphere, oceans, ice sheets, continents, and a dynamic interior. Each of these components moves and redistributes mass over time. As a result, the balance of the rotating planet is constantly adjusting. The Chandler wobble represents one of the most visible expressions of that adjustment. When Seth Carlo Chandler first identified the oscillation, the cause was not immediately understood. Some scientists suspected it might arise from movements within the mantle or from changes in atmospheric pressure. Others proposed that ocean circulation might play a role. Over the following decades, improvements in observational techniques allowed researchers to measure the motion of the pole with increasing precision. By the mid-20th century, it became clear that the Chandler wobble could not be explained by a single process. Instead, it reflects the combined influence of many processes occurring throughout the planet. The physics behind the wobble is related to the moment of inertia of Earth. When mass shifts relative to the rotation axis, the axis responds by adjusting its orientation in order to conserve angular momentum. This adjustment produces a small circular motion of the pole across the surface. Several factors contribute to these shifts. One major influence comes from the oceans. Ocean currents move enormous volumes of water across the planet. Seasonal variations in circulation redistribute mass between different regions of the ocean basins. These changes alter the balance of the rotating Earth and contribute to the motion of the pole. Another important factor is the atmosphere. Changes in atmospheric pressure move large masses of air across continents and oceans. When pressure systems strengthen or weaken, the distribution of atmospheric mass changes. This redistribution influences the position of the rotation axis. The cryosphere also plays a role. Ice sheets and glaciers store vast quantities of frozen water near the poles. When these ice masses grow or shrink, the distribution of mass across the planet changes. Melting glaciers transfer water from polar regions into the oceans, shifting weight toward lower latitudes. In recent decades, satellite missions have provided a powerful new way to observe these processes. The Gravity Recovery and Climate Experiment mission, developed by the National Aeronautics and Space Administration and the German Research Center for Geosciences, measures tiny variations in Earth's gravitational field. These measurements reveal where mass is increasing or decreasing across the planet. By tracking changes in gravity over time, scientists can observe how water moves through the oceans, glaciers, and underground aquifers. When researchers compare these gravitational measurements with records of polar motion, they find clear connections. Movements of water and ice produce measurable shifts in the position of the rotation axis. The connection between mass redistribution and polar motion was further confirmed through satellite geodesy. Networks of satellites equipped with laser ranging systems measure the exact distance between spacecraft and ground stations. These measurements allow scientists to determine the orientation of Earth in space with extraordinary precision. Using these tools, researchers have shown that variations in ocean circulation and atmospheric pressure explain a large portion of the Chandler wobble's behavior. However, the wobble does not persist indefinitely without external influence. In theory, friction within the Earth's system should gradually damp the motion. Yet the oscillation continues decade after decade. This persistence indicates that energy from ongoing processes continually excites the wobble and sustains it. Ocean circulation appears to provide a significant portion of this energy. Large-scale current systems, such as the Pacific and Atlantic circulation patterns, shift mass through the oceans on seasonal and interannual timescales. These movements reinforce the oscillation and keep the wobble active. Atmospheric processes also contribute energy to the system. Changes in global wind patterns redistribute atmospheric mass and interact with the rotation of the planet. These changes influence the orientation of the rotation axis. Carl Sagan once remarked on the remarkable precision required to understand planetary motion when he said, "Extraordinary claims require extraordinary evidence. The study of polar motion illustrates how careful measurement can reveal subtle aspects of planetary behavior that would otherwise remain hidden." Over more than a century of observations, scientists have tracked the Chandler wobble with increasing accuracy. The oscillation has become a valuable tool for studying the dynamics of the Earth system. By analyzing how the wobble evolves over time, researchers gain insight into how mass moves through the oceans, atmosphere, ice sheets, and interior of the planet. The motion of the pole acts as a sensitive indicator of changes occurring across the entire Earth system. In recent decades, scientists have noticed that the characteristics of the wobble appear to be changing slightly. The amplitude and direction of polar motion have shifted in ways that suggest evolving patterns of mass redistribution. Some studies link these changes to accelerated melting of glaciers and ice sheets. As ice mass declines in Greenland and Antarctica, the redistribution of water influences the orientation of Earth's rotation axis. Other research suggests that changes in ocean circulation may also contribute. Variations in currents can shift large masses of water across the globe, altering the balance of the rotating Earth. These observations reinforce the idea that the Chandler wobble reflects the integrated behavior of the entire Earth system. The oscillation captures the combined influence of processes occurring in the atmosphere, oceans, cryosphere, and solid Earth. What makes this phenomenon especially valuable to scientists is its sensitivity. Even relatively small changes in mass distribution produce measurable shifts in the position of the pole. As measurement techniques improve, the wobble provides an increasingly detailed record of how the planet evolves over time. Modern geodesy now relies on a global network of observations including satellite tracking, laser ranging, and radio astronomy measurements of distant quasars. These methods establish an extremely stable reference frame against which Earth's orientation can be measured. Within that reference frame, the Chandler wobble appears as a slow circular motion of the rotation axis relative to the surface of the planet. The diameter of the motion remains small, yet its scientific significance is enormous. It reveals that Earth behaves not as a rigid spinning sphere, but as a dynamic system in which mass moves continuously through multiple interconnected reservoirs. As researchers continue to analyze satellite observations and global geophysical data, the Chandler wobble remains one of the most sensitive indicators of how the planet is changing. The motion of Earth's rotational pole already records how mass slowly redistributes across the planet. Yet a far more precise view appeared once two satellites began mapping extremely small variations in Earth's gravity, measurements that made it possible to follow the movement of the planet's mass in real time, an idea explored further in Why Do Satellites Now Watch the Planet's Weight Move in Real Time? A planet weighing nearly 6 sextillion kilograms appears unchanging from the ground. Yet modern satellites have revealed that the weight of Earth shifts constantly as water, ice, and rock move across its surface. Since the early 21st century, a pair of orbiting spacecraft has been quietly measuring these movements by detecting minute variations in the planet's gravitational pull. Those measurements have transformed our understanding of how mass migrates across Earth and how these migrations influence the rotation of the planet itself. The mission responsible for this breakthrough began in March 2002, when the National Aeronautics and Space Administration, working together with the German Research Center for Geosciences, launched the Gravity Recovery and Climate Experiment satellites. The spacecraft traveled in the same orbit around Earth, separated by roughly 200 kilometers. Their purpose was deceptively simple. By tracking the distance between them with extraordinary precision, scientists hoped to map tiny variations in Earth's gravitational field. Gravity is often described as a force that pulls objects toward the center of a planet. Yet the strength of that pull is not perfectly uniform across Earth. Regions containing greater amounts of mass exert slightly stronger gravitational attraction, while regions with less mass exert slightly weaker attraction. Mountains, ocean trenches, dense rock formations, and large ice sheets all influence the local gravitational field. Even changes in water storage within river basins and underground aquifers produce detectable variations. The Gravity Recovery and Climate Experiment satellites measure these variations using a remarkably precise technique. As the spacecraft orbit the planet, the leading satellite encounters changes in gravity first. When it passes over a region containing more mass, the gravitational pull becomes slightly stronger, causing the spacecraft to accelerate forward. A fraction of a second later, the trailing satellite experiences the same change. By measuring the tiny difference in distance between the two spacecraft during these encounters, scientists can determine how the gravitational field varies beneath them. The distance measurements are astonishingly precise. Instruments aboard the satellites detect changes smaller than a few micrometers. This level of sensitivity allows researchers to map variations in gravity caused by shifts in mass equivalent to only a few centimeters of water spread across large regions of Earth. When the mission began transmitting data, scientists quickly realized that they were observing the movement of water across the planet in a way never before possible. Glaciers shrinking in Greenland produced clear signals in the gravitational maps. As ice melted and flowed into the ocean, the local gravitational field weakened because mass had been removed from the ice sheet. Similar patterns appeared in Antarctica, where several major glaciers were losing ice at accelerating rates. At the same time, the satellites detected changes over continental regions where groundwater was being extracted from underground reservoirs. Aquifers in northern India, the North China Plain, and parts of the United States showed measurable declines in mass corresponding to the removal of water for agriculture and urban use. The mission also revealed seasonal cycles of water storage across large river basins. During wet seasons, water accumulates in soil, lakes, and rivers, increasing the gravitational signal. During dry periods, that mass decreases as water evaporates or flows toward the ocean. For the first time, scientists could observe the entire hydrological cycle of Earth through direct measurements of mass redistribution. These observations carried an unexpected implication for planetary rotation. Every time water moves from one region of Earth to another, the distribution of mass relative to the rotation axis changes. Because angular momentum must be conserved, the rotation of the planet responds to those changes. Geophysicists studying polar motion began comparing the satellite gravity data with records of the movement of Earth's rotational axis. The comparison revealed a striking result. Roughly 90% of the fluctuations in polar motion could be explained by the redistribution of water and ice across the surface. This finding demonstrated that processes occurring within the hydrosphere and cryosphere play a dominant role in shifting the balance of the rotating Earth. The implication was profound. Climate-related processes such as glacier melt, changes in groundwater storage, and large-scale ocean circulation were not only environmental phenomena. They were also contributors to the mechanics governing Earth's rotation. One of the most dramatic signals observed by the gravity recovery and climate experiment satellites came from Greenland. The ice sheet covering the island contains enough frozen water to raise global sea level by several meters if it were completely melted. Satellite measurements revealed that Greenland has been losing hundreds of billions of tons of ice each year. When that ice melts, the resulting water flows into the ocean and spreads toward lower latitudes through global ocean circulation. This transfer of mass alters the moment of inertia of the planet. As water moves away from polar regions toward the equator, the rotational balance of Earth changes. The axis adjusts slightly in response. Similar signals appear in Antarctica, although the patterns are more complex due to the vast size of the continent and the interaction between ice shelves and the surrounding ocean. The gravity recovery and climate experiment satellites also detected significant groundwater depletion in agricultural regions around the world. When water is pumped from underground aquifers and eventually reaches rivers and oceans, the mass distribution of the planet shifts. Each of these processes contributes a small component to the overall motion of Earth's rotational axis. Carl Sagan once described the power of observation in science with the statement, "Science is a way of thinking much more than it is a body of knowledge." The success of the gravity recovery and climate experiment mission illustrates this principle clearly. By focusing on precise measurements of gravitational variation, scientists opened an entirely new window into the dynamics of the Earth system. The original mission operated for 15 years before ending in 2017. During that time, it produced one of the most detailed records ever assembled of how mass moves across the planet. Recognizing the importance of this data, the National Aeronautics and Space Administration and the German Research Center for Geosciences launched a successor mission known as Gravity Recovery and Climate Experiment Follow-On in 2018. The new spacecraft continue the work of measuring Earth's gravitational field with even greater precision. Together, these missions have transformed geophysics by providing direct observations of how water and ice redistribute across the planet over time. The connection between these movements and Earth's rotation demonstrates the deep interconnectedness of planetary processes. Oceans, glaciers, groundwater reservoirs, and atmospheric circulation all contribute to the evolving balance of mass that governs how the planet spins. Each year, new satellite data refine our understanding of these relationships. Researchers now monitor polar motion, gravitational changes, and rotation variations with unprecedented accuracy. The ability to watch the weight of the planet shift in near real time has turned Earth itself into a dynamic laboratory where the movement of mass reveals the physics shaping the behavior of the entire system. These measurements continue to be studied carefully by scientists. As the data accumulates, the observations begin to point toward a broader issue involving time itself. If the redistribution of mass and momentum keeps altering the speed of Earth's rotation, the implications eventually reach the foundations of global timekeeping, an issue explored further in If the length of a day keeps changing, what happens to time itself? For thousands of years, humanity believed time was written in the sky. The rising sun marked morning. The stars crossing the night sky marked the passing of hours. And the rotation of Earth itself defined what we called a day. It seemed perfectly natural that the spinning of our planet would serve as the clock for civilization. But modern science eventually revealed a quiet problem. Earth does not rotate with perfect regularity. Tides raised by the moon slow the planet over long timescales. Winds, ocean currents, and movements within the molten core shift angular momentum between layers of the planet. The result is subtle but measurable. The length of a day is not constant. By the middle of the 20th century, this irregularity had become impossible to ignore. Astronomers comparing Earth's rotation with precise astronomical observations noticed that the planet's spin wandered unpredictably. Some days were a little longer. Others were slightly shorter. The differences were tiny, measured in milliseconds, but they accumulated over time. This discovery forced scientists to rethink one of the most basic quantities in physics. What exactly is a second? For centuries, a second had simply been defined as a fraction of a day. Divide Earth's rotation into 24 hours, each hour into 60 minutes, each minute into 60 seconds. The definition felt natural because it was tied directly to the motion of the planet beneath our feet. But once scientists realized that Earth's rotation drifts, a new standard was needed. The solution came from the microscopic world. Inside atoms, electrons occupy specific energy levels. When an electron shifts between two particular states, it emits or absorbs radiation with a frequency that is extraordinarily stable. In 1967, the international scientific community adopted a new definition. 1 second would no longer depend on the rotation of Earth. Instead, the second would be defined by the behavior of cesium atoms. More precisely, 1 second equals the time required for 9,192,631,770 oscillations of radiation associated with a specific transition in the cesium-133 atom. This definition might sound technical, yet its meaning is simple. Time is now measured by the steady rhythm of atomic physics. These devices are known as atomic clocks, and they are among the most precise instruments humanity has ever built. The best modern clocks would lose less than a second over tens of millions of years. Their stability is so extraordinary that they have become the foundation for global navigation systems, telecommunications networks, financial markets, and scientific experiments across the planet. Yet, despite this atomic precision, human society still lives according to the turning of Earth. Civil time is coordinated through a system called Coordinated Universal Time. This global standard attempts to keep atomic time synchronized with the position of the sun in the sky. Noon should still occur when the sun stands highest above the horizon. To maintain this alignment, adjustments are occasionally required. These adjustments are called leap seconds. Whenever Earth's rotation drifts too far from atomic time, scientists add an extra second to the global clock. On such nights, the final minute of the day contains 61 seconds instead of 60. The additional second gently nudges civil time back into alignment with the spinning planet. Since 1972, more than 24 leap seconds have been inserted. Until recently, however, all leap seconds moved in one direction. They added time because Earth's rotation was gradually slowing. Now a new possibility is emerging. In recent years, scientists have observed several days in which Earth rotated slightly faster than expected. The difference was small, only fractions of a millisecond, yet the trend surprised researchers who study the dynamics of our planet. If these fluctuations continue, a situation could arise that humanity has never faced before. Instead of adding a second to the global clock, scientists might need to remove one. This adjustment is known as a negative leap second. Rather than stretching the last minute of the day to 61 seconds, the clock would skip directly from 59 seconds to the next minute. 1 second would vanish from the official record of time. It would be the first moment in history when the global timekeeping system deletes a second rather than adding one. The idea may sound simple, but its implications are surprisingly complex. Modern technological systems depend on extremely precise time synchronization. Satellites transmitting navigation signals must coordinate their clocks with extraordinary accuracy. Financial transactions across global markets rely on timestamps measured to microseconds. Data networks guiding the flow of information across continents assume that time moves forward in perfectly ordered steps. Even a single missing second must be carefully managed to prevent errors. For this reason, international timekeeping organizations study Earth's rotation with extraordinary care. Observatories around the world track the planet's orientation in space using radio telescopes, satellite laser ranging, and space-based geodesy missions. Data from systems such as the Gravity Recovery and Climate Experiment satellites reveal how water, ice, and atmosphere shift across the planet's surface. Each movement redistributes mass and subtly influences Earth's spin. Through these measurements, scientists have learned something remarkable. The length of a day is not controlled by a single process. Instead, it reflects the combined behavior of the entire Earth system. Ocean currents sliding across the globe, atmospheric winds racing through the upper sky, melting ice sheets, shifting groundwater, and slow motions inside the deep mantle all contribute small adjustments to the planet's rotation. When these processes interact, the result appears in the most familiar rhythm of human life. The cycle of day and night. What once seemed perfectly steady is actually the outcome of countless moving parts. a dynamic planet constantly redistributing energy and mass beneath our feet. And because of that motion, the definition of time itself must adapt. Carl Sagan once reflected on humanity's attempt to measure the universe with precision. He wrote, "Somewhere, something incredible is waiting to be known." In the case of Earth's rotation, the incredible discovery is that even our most familiar clock, the turning of our own planet, remains part of an evolving physical system. Tonight, we followed that system through oceans, atmosphere, ice sheets, and the deep interior of Earth. Each layer left subtle fingerprints in the rhythm of planetary rotation. Together, they reveal a world that is not static, but constantly adjusting, responding, and moving. Thank you for spending this time exploring the science of our restless planet. If this quiet journey through Earth's hidden mechanics brought you a moment of curiosity or calm, I truly appreciate you being here. A gentle subscribe is the encouragement that allows these long explorations of science to continue. And as the planet beneath us continues its slow and subtle motion through space, I hope the rest of your night is peaceful, your thoughts settle easily, and your sleep comes naturally beneath the turning sky.